The reaction quotient Q and the equilibrium constant K can both be used to mathematically explain and justify the Le Chatelier principle. This is part of Unit 7 in AP Chemistry on Equilibrium, Topic 10, but it could be part of your college-level chemistry course. In this one page of notes, I will be doing an example problem to prove that the established equilibrium can be stressed, and when it alleviates that stress, we will still get the same value for K, but with a new set of equilibrium concentrations or partial pressures called an equilibrium position. The reaction that we're going to do involves iodine and chlorine, making iodine monochloride as the product. And the original pressures for our reactants are both 0.028 atm partial pressures. And so these are already at equilibrium. These are the established equilibrium partial pressures. And then for the iodine monochloride, it's 0.25 atm. What I'm going to first do is write down the Kp value, the equilibrium expression, and calculate the equilibrium constant with these established equilibrium partial pressures. So the Kp is just an equilibrium based off of partial pressures, and I do talk about this in other videos. You have your products on the top, the partial pressure of our iodine monochloride, and then squared due to the coefficient in front of the iodine there. And then on the bottom, or on the denominator, you have the partial pressure of the iodine. You can put it to the first power, but most people don't write that, and the partial pressure of the chlorine to the first power. And so our original Kp, our established equilibrium with these established partial pressures, is 0.25, and then squared, and then divided by 0.028 both times, 0.028, which you could just square that, but that's the partial pressure. I'm just leaving the units out because equilibrium constant does not have a unit. And I do talk about that in other videos that I have. And then the Kp is just, we're going to say 80, and if you want to put a dot with 2 sig figs. So that's our original equilibrium constant is 80, which means that it favors the production of product, or it would be product favored. All right, so if we read the problem, what happened then is we stressed our equilibrium. It's at equilibrium at this point, but then we added in and we increased the partial pressure of the iodine monochloride to 0.35. So the first thing that happened was we put in our 0.35 atm for our product, so that the product concentration went up. And then our initial concentrations for these two did not change. So we didn't add anything different for our reactants. We just put some increase in the iodine monochloride. So then what's going to happen is it's going to shift a certain direction. Let's just check by calculating the Q. You might already have an idea since you maybe have learned about Le Chatelier's principle, but let's mathematically prove everything this time in this set of notes. So the Q value we calculated the same as the K. So we're still going to have the partial pressure of the iodine monochloride in the numerator squared, the partial pressure of the iodine, and the partial pressure of the chloride in the denominator. But we're going to put in our initial set of concentrations, so 0.35 atm, but we'll skip the unit. And then 0.028, and just to save room, that's going to be squared. And this is going to give us approximately 156. And what that means now is that the Q value is greater than the K, and you might have learned this in a different set of topics. So that means it's going to shift to the left, which means we have to produce more reactant and decrease our product amount. What that allows us to do is put in our minus X and plus X values in the C per the change column of our data table up here. So we're going to say it's going to lose twice as much of that and gain our reactants in a 1-to-1 mole ratio. So then our 0.028 is going to be plus X, where a lot of times it's minus 0.028 plus X, and then 0.35 minus 2X. And I'll come back to put the final values in for the equilibrium amounts right here in ATM. But that's going to be at the end of the problem. So this is just kind of a different rice table that we can use with the reaction, initial, change, E with the X, or equilibrium with the X value, and this is without. And then again, remember this equilibrium was already established, and those were the equilibrium partial pressures at the start. All right, so let's just try to solve this. So we know that it has to shift, but we know that it's still going to have to equal 80. Okay, so what happens with this one is we're going to say the Kp will reestablish with a new equilibrium position to equal 80, but we're going to have 0.35 minus 2x in the numerator squared, and then 0.028 and then plus x, but twice, so that one is also squared. We can use the law of what's called perfect squares, which means that we're just going to take the square root of both sides. So we're going to take the square root of 80, and then we'll take the square root of everything that's inside of here. I'll just write it again. Since I'm only going to do one problem, it's going to be kind of a one and done with this one. And the whole point here is to try to prove that Le Chatelier's principle is correct. All right, so when this is all done here, I'm just going to go over to the side here. We got the square root of 80. I'm just going to leave that. And then that's going to equal 0.35 minus 2x, and then divided by 0.028 plus x. And then I'm just going to do a little bit of algebra or math, and I'm going to put the this part here. We're going to put it onto the other side here, so we're going to multiply both sides by that. And that would leave then the 0.35 minus 2x, okay? And I'm just going to move down to the middle here because it's going to be a little bit long. We're going to then have to distribute things through and also then move some values over, okay? So the first thing we're going to do is take the square root of 80 and multiply it by that, okay? And that's going to give us 0.250 and then plus 8.94x, okay? And this, when you take the square root of that, it is the 0.894. And then that's going to equal 0.35. So we really haven't done anything to the right side of this equation. And then the next thing we're going to do is combine kind of our terms. So we're going to have the 2x on this side plus the 8.94x. Got a great use for algebra here. And then 0.35 and then minus the 0.25. And we can even just get rid of that sig fig. And then this is going to equal 10.94x. And that's going to equal 0.100. And if you divide this out, x will give us 0.00914. Kind of carry an extra sig fig there. So then what we're going to do is kind of solve for each concentration separate. So the partial pressure of the iodine, or you know, in this case, partial pressure instead of concentration. These could be, you know, brackets and molarity, but this problem I wanted to keep it with ATMs. So we're going to start out with 0.028, and then remember we gained then the x, which would be 0.0091, and then same for the chlorine, and then 0.0091. So those are going to be the same value, and I'll put them back up at the top what they equal. And then last, the iodine monochloride is going to be then, and then don't forget, it's going to be 2 times the 0.0091, because that was 2x. And then those values, I'm just going to kind of go like this. These values, I'm going to put back up at the top what they equal. And then I'm going to put them back into the equation and just check that they do give us approximately 80. And we have a new set of concentrations, or in this case, partial pressures, at equilibrium. All right, so I'm going to write them actually in green. So 0.0371 ATM for this one. And these will all be the same. And you can see that that went up compared to where it was before the equilibrium was, you know, stressed. It alleviated that stress by increasing the concentration of the reactant and decreasing the product. However, the product doesn't go below its original. It still is higher. You know, so its original was 0.25, but it does go down, and it went down to 0.332. All right, so those are the three values I'm going to put back into the equation. I'll do that actually in green. So down at the bottom here, I'm going to put those into the Kp. So the original one was 0.332 for the new constant, or the new partial pressure for the iodine monochloride, and then the 0.0371, and there was both of those. And if you do check again, just to kind of remind you, this is the partial pressure of the iodine monochloride, and then the partial pressure of the iodine, and and the partial pressure of the chlorine. So we're still using the same K expression. And then what happens is this gives us approximately 80 if you check. And so that's going to be called a new equilibrium position. So equilibrium position. And it does relate to a previous video I have on equilibrium positions, that sometimes you can have different values that'll still give you the same K value. So this is still going to be 80, but we have different values in for our partial pressures of our reactants and products. So that's kind of proving that Le Chatelier's principle is correct, in that if we read kind of the beginning here, that if we have a product and we add it to an established equilibrium, the product will decrease in its amount, shift left, which means it's going to produce more reactant, and then that reactant amount will go up, the product amount will go down, but not below the amount that we had before, just down lower than what we had as an influx of that product in the reaction. All right, so I hope this one page of notes helps you understand 7.10 in AP Chemistry, and feel free to watch other YouTube videos I have on Unit 7 and on to 7.11 and 12 with the equilibrium of solubility of partial products, or solubility products, and then also common ion effect.